Before we get into it, I want to set expectations. This isn't a tutorial, it's not a teardown, it's not a step by step guide. What I'm sharing here is something slower, a space to think about how we build systems and sometimes how they fail. If you work with embedded tech, design for healthcare, or just find yourself wondering how we could do things differently, I think you'll feel at home here. And if you're here for a quick how to or a parts list, that's totally fine. There are plenty of great videos out there for that, just not this one. Now, let's start our video. Today, I've been thinking about something simple on the surface, but that keeps showing up in the background of the work I care about. Some systems can fail, others really can't. A pacemaker, not just any embedded system, one designed to never stop, and yet, even pacemakers can fail. Battery depletion, rare firmware bugs, interference, these events are rare, but not impossible. And that's the point. When failure isn't an option, the system must be designed like it. A Holter monitor, it doesn't sustain life, but it must capture every beat. If it misses too much, the diagnosis could be wrong or lost. It's not a catastrophic, but it's costly and sometimes preventable. A rehab tracker, a home monitor running quietly overnight. These aren't as critical yet, but they are moving closer to that line. The more we rely on them for real care, real feedback, real intervention, the more their failures will matter too. So here is the question I keep circling back to. Should a system that absolutely can't crash run an operating system? And RTOS feels like a safe choice. Structure, tasks, timers, priorities. It helps manage complexity, especially as systems scale. But every layer brings weight. More abstraction, more code paths you didn't write. There are more places where things can quietly unravel. We've all seen it. An ISR that doesn't fire, a scheduler bug that only shows up under load, a task that silently starves out the one doing something critical. Bare metal, by contrast, gives you control. You own the flow. You know the shape of the system. But then the system grows. You add Bluetooth or a second sensor, maybe a learning module, and suddenly that tidy loop starts to bend, or worse, break. And this isn't theoretical. We are already building systems that ask for harder things of smaller hardware. In a recent video, I explored whether a clinical decision support system, the kind that usually built for hospitals, could run entirely at the edge. No cloud, no backend, just logic, close to the patient. That was the dream, but it raised another challenge. What does the operating system cost us? Not in money, in timing, in predictability, in power you don't get back, in confidence you can't afford to lose. Because when you are building the edge, and the edge is a wristband or diagnostic device, every layer must justify itself, even the operating system. So maybe the real question isn't RTOS or bare metal. Maybe it's, can we design systems that scale down without falling apart? Where the operating system isn't a default, it's a choice. Where a task manager doesn't just work, it explains itself. Where every layer is small and clear and human understandable. And sometimes the danger isn't in failing, it's in acting when you shouldn't. That's something we explored in another video. How false alarms in ICU monitors create alarm fatigue, and how sometimes the smartest thing is a system can do is nothing. Inaction in those cases isn't passive, it's a decision, a design choice. So when we talk about safety, we're not just talking about uptime, we're talking about judgment and design, about what a system does and what it deserves to do. So, yes, maybe this started with the question, should a system that can't crash use an operating system? But the real question is this: what kind of systems do we want to trust when there is no one left to catch them? That's where I'm with it. Let me know where it takes you.